Designing a fifth-generation stealth fighter from a blank sheet of paper is one of the most punishing engineering challenges a nation can undertake. India's answer to this challenge is the Advanced Medium Combat Aircraft, or AMCA. It is planned as a 25-ton class, twin-engine, multirole stealth fighter. The program is driven by a strict operational necessity. The Indian Air Force requires a highly survivable platform to eventually replace its aging heavy fighter backbone. Specifically, the AMCA is tasked with supplanting the Sukhoi Su-30 MKI, an air superiority fighter that anchors the IAF fleet but lacks modern low observable characteristics. To effectively replace the Su-30 MKI in modern contested airspace, the AMCA must achieve two non-negotiable aerodynamic parameters: a low radar cross-section and the ability to supercruise, maintaining supersonic flight without the use of fuel-heavy afterburners. Building a platform to these specifications requires abandoning iterative upgrades. The engineering teams must cross three distinct technological thresholds simultaneously. They must master multispectral stealth integration, develop indigenous high-thrust propulsion intellectual property, and construct fully AI-assisted avionics architectures. Conquering these three domains represents the only viable path for India to transition from a buyer of legacy platforms into an independent aerospace power capable of sovereign defense manufacturing. The first of these thresholds is aerostructural stealth integration. Evasion of enemy radar is primarily a function of macroscopic geometric design. The physical shape of the airframe dictates survivability long before radar-absorbent coatings are applied. This 3D wireframe illustrates the AMCA's structural baseline. Engineers utilized diamond-shaped wings and a V-tail layout to deflect electromagnetic waves. Microscopically, the geometry relies on strict platform edge alignment. The bay doors feature serrated edges, meticulously calculated to scatter residual radar waves. Even with perfect external geometry, every jet engine introduces a massive radar vulnerability: the highly reflective nature of rapidly spinning metal. If an enemy radar pulse strikes the exposed turbine fan blades, the signal bounces straight back, completely compromising the aircraft's stealth profile. To solve this, the AMCA utilizes diverterless supersonic inlets paired with S-shaped serpentine ducts. This comparison diagram demonstrates the physics. A straight duct allows waves to hit the fan blades and return. However, the S-shaped duct forces radar waves to bounce repeatedly off internal radar-absorbent walls. Reaching the fan blades, the energy has entirely dissipated. The AMCA's physical shape operates as a mathematical equation, literally carved by the physical laws of radar deflection. With the geometry established, the engineering focus shifts to the materials science of the aircraft's skin. To further suppress radar returns and reduce weight, 38 to 40% of the AMCA's total airframe structure will be manufactured using advanced composites. Additionally, researchers at IIT Kanpur have developed a metamaterials surface cloaking system, or MSCS, designed specifically for this program. This metamaterial operates by actively absorbing electromagnetic waves across a wide synthetic aperture radar spectrum, providing true multispectral camouflage. But an aircraft must carry lethal mass, and adding external weapons immediately threatens this carefully crafted low-observable profile. This forces a division in operational modes: strict stealth for first-day-of-war penetration missions versus a non-stealthy configuration where munitions are mounted on external hardpoints. This chart details the resulting payload disparity. In its stealth configuration, the AMCA is limited to a 1,500-kilogram capacity within its internal weapons bay. Once air superiority is achieved, it can utilize its external stores to carry an additional 5,500 kilograms of ordnance. Strapping missiles to the exterior instantly compromises the radar cross-section, making the smaller, enclosed internal weapons bay a strict requirement for deep strike stealth operations. Every millimeter of the AMCA structure is a calculated compromise, balancing the need to carry lethal payloads against the physical requirements of remaining invisible. The second engineering threshold is propulsion. The mathematics of thrust to weight are unforgiving. Pushing a 25-ton fighter through the sound barrier efficiently requires immense power. To meet its strict supercruise parameters, the AMCA requires engines capable of generating greater than 105 kilonewtons of thrust. Because developing a high-thrust engine takes decades, the program relies on a phased production approach, beginning with the Mark I variant. The Mark I will be powered by the U.S. origin General Electric F-414 engine. Generating 98 kilonewtons of thrust, this existing hardware falls short of the aircraft's ultimate aerodynamic requirements. The definitive solution rests on the AMCA Mark II, which will utilize a new joint venture engine targeting an output between 120 and 140 kilonewtons. The diplomatic framework allowing for this co-development is the Horizon 2047 roadmap, a strategic partnership established between India and France. This political alignment facilitates a deep technology transfer from the French aerospace firm Safran to India's Defense Research and Development Organization. To manufacture this engine, the Indian Gas Turbine Research Establishment must overcome a specific, highly complex material science hurdle: the mass production of single crystal blade technology. Single crystal blades are strictly necessary. Traditional metallic structures will melt or deform under the extreme heat and mechanical stress inside a 120 kilonewton turbofan. The ultimate goal of the Safran partnership is a 100% transfer of intellectual property rights, enabling fully sovereign domestic manufacturing of these engines. The nation that controls the engine IP controls the operational fleet. The Mark II engine agreement secures the necessary thrust, and it secures national sovereignty. The final engineering threshold centers on avionics and sensor fusion. The AMCA cockpit utilizes a single-seat configuration. There is no human co-pilot to manage the radar or weapon systems. Operating a fifth-generation fighter requires simultaneously managing multispectral stealth profiles, complex propulsion telemetry, and electronic warfare suites, creating a severe cognitive overload for a single pilot. To solve this, the cockpit features a large area display developed by Data Patterns India, powered by an underlying electronic piloting system. Instead of relying on a single nose-mounted radar, the AMCA utilizes distributed passive sensors to continuously collect raw data from across the entire airframe. As illustrated here, these disparate sensor nodes funnel millions of data points into a centralized processing hub. An onboard artificial intelligence executes sensor fusion on this data, automatically identifying threats and filtering the information before presenting it to the pilot. The AI acts as the virtual co-pilot. The pilot's decisions are then physically executed by highly precise domestic hardware, such as stability actuators developed by Godrej. The AMCA operates as a flying, AI-driven data processing node, analyzing the battle space as much as it navigates it. Moving the AMCA from a digital model to an active squadron requires tearing down and restructuring India's defense manufacturing ecosystem. Historically, the Indian aerospace procurement relied almost exclusively on Hindustan Aeronautics Limited. This public sector monopoly created a severe bottleneck, with production consistently hampered by an overloaded order book. To prevent these delays, the Aeronautical Development Agency introduced a new execution model. They issued an expression of interest to establish industry partnerships through a special purpose vehicle. This chart maps the transition to a decentralized model, moving away from a linear monopoly. Manufacturing is dispersed to private consortia like L&T, Bharat Forge, and Tata. By utilizing these partners for rapid prototyping and lifetime maintenance, the program avoids legacy production delays. This restructuring extends to the physical geography of the program. To streamline operations, a dedicated flight testing center and assembly line is being established at Puttaparthi in Andhra Pradesh. Under this decentralized approach, the program projects its first prototype flight between 2028 and 2029, full certification by 2032, and series production by 2035. The Advanced Medium Combat Aircraft is a fifth-generation fighter program, but operationally it serves as the ultimate stress test, one designed to definitively modernize India's entire indigenous aerospace manufacturing base.